Greetings and welcome to our poster review for CLOVIDD, which is the Coronavirus Location, Oxygen Saturation, Verification of Temperature, and Individual Pulse Rate Detection Device. Group members are Matreyi Joshi and Stephen Starwitz. To give you a brief introduction of what we proposed, we looked at some resources. After coronavirus reared its ugly head in the United States, they seem to talk about a correlation between patient oxygen saturation levels and an unexpected need for medical attention. So we proposed a device that would be able to collect such information and relay it over an IoT pathway after being anonymized to a database to allow correlation of different locations of the users. We proposed a particular device that had a MAX 30102 sensor, which is both a pulse rate and pulse oximeter, which detects the level of oxygen present in capillaries and blood vessels. For this particular operation, we used a finger as the desired collection point for both that heart rate and that O2 saturation level. There were a number of components as shown in this particular image here. In the brown, you have the wearer/patient. In gray, you have our server for administrative review of the GPS locations of the anonymized data. You have a microcontroller that handles all the communication between the sensors. And here we have the oximeter and pulse sensor, and you also have a temperature sensor. Feedback to the user is a buzzer and an LED. And we have the GPS module over here and a LoRa transceiver with its associated antenna, making the connection to the server. We utilized UART, I2C in our particular design. And based on the number of sensors we had and the modules that we intended to integrate with our microcontroller, we developed a product schedule based upon a week 0 ordering parts, and then weeks 1 through 3 generally dealt with the LoRa gateway, creation of the server, and then weeks 4 through 7 generally dealt with integration of these sensors, the feedback to the wearer/patient, and also the GPS module interfacing with the microprocessor. We broke down our deliverables into 2 different sections, one of them being basic connectivity. Can we get data from our sensors? Can we get data from our GPS module? Can we write data to the LoRa transceiver? After that, we looked at the verification of the data based upon a human test subject to see if the data made sense.
Let us now look at the Arduino working with all the sensors. It takes few moments for the system in whole to stabilize. Once stabilized, the system starts showing the output on the serial monitor of the Arduino. The HR and the SpO2 represents heart rate and oxygen level values respectively, along with the temperature values. By keeping our finger on the heart rate and oxygen level sensor along with the temperature sensor, we get the corresponding values as shown. The temperature values which we are able to see right now are not exact since our finger does not have the same temperature as our body does. Therefore, since it is a contactless temperature sensor, we can measure it on our forehead. The GPS sensor takes some time to give the output. To get the alerts via LED and buzzer, we have to decide a threshold value for the oxygen level and the temperature.
As a part of our results section, our rather lengthy results section, we realized that a number of things were trickier than anticipated in integrating all these sensors and GPS module into a single unit. One of the things we noted is that the O2 and pulse rate readings coming from the sensor are raw data coming out of a first in, first out FIFO I2C register, and the algorithm that looks at those to see where the heart rates are, looks for a sudden drop in a particular value that is associated with a sinusoidal heartbeat. So you have your initial squeeze, and then you have a retraction as the ventricles fill with blood. And that is what you see borne out in the various blood vessels and capillaries when excited with a red and infrared light that allows for recognition of both the pulse and the O2 saturation levels, respectively. We were unable to get a pulse rate that was consistent with a seated individual operating between 60 and 80 beats per minute. Many of our numbers were jumping into the 150 to 200 beats per minute range. So we discovered that there was an error with our processing algorithm that was preventing us from getting appropriate data. We also realized that in our GPS module, the NMEA sentences, which were provided from the GPS module via the UART pathway, we needed to parse them in a particular way to get the latitude, longitude, and time of the particular location. Sometimes we would attempt to read it and would be unable to find that particular sentence, would move on in our program, and would miss the sentence for a lengthy period of time. Our longest time until finding a fix was 30 minutes, which is impractical for someone wearing this and having a location that needs to be sent via an IoT pathway to a server. We also found that the microprocessor we selected, which was an Arduino Mega 2560, was unable to interface properly with our LoRa transceiver. The LoRa transceiver we used in class was based upon a connection with the Launchpad 2650 XL, which is a Texas Instruments microprocessor and its associated peripherals, and that was the only way that we could communicate with the LoRa transceiver. So we were unable to communicate between the microprocessor and the LoRa transceiver because the Launchpad has only one UART port, which was tied up by the LoRa transceiver and was not available for us to interface with it. And lastly, our server, we initially had attempted to set up something on a site called IoT Gecko. This site proved to be unsuitable for what we were trying to do. An additional attempt was made for Amazon Web Services to find a server that was appropriate for our data use. Instead of any of those, we wound up using something called Google Firebase, which at this point, since we've been unable to interface our microprocessor with our LoRa transceiver, we have only been able to gather data from our microprocessor using serial over USB. In conclusion, we found that our key takeaways are we need to ensure that the sensor data is viable and is appropriate for the use case. We also need to understand how to integrate multi-channel data gathering on a microprocessor that is a single thread, that does not have a breadth of interrupts available to it, and for sensors and GPS modules that are sending data at different rates. And lastly, we need to be able to package the data that we received after processing and send it out via the LoRa transceiver. Unfortunately, all three of those ran into difficulty, and we were unable to produce the device that we had initially set out to in our project proposal. As such, our future work section talks about looking at the GPS sentence retrieval and looking for additional ways to gather that data. For some of the GPS modules that are available, they have what is called a display data channel, which is a I2C compliant data bus that may allow us to put all of the sensors and the GPS module on the same I2C bus that we've been using for this entire project. If that is the case and we are able to request data from the register as expected, that alleviates our issue of missing the NMEA sentences and allows us to incorporate that GPS data immediately into variables inside of our microcontroller. We also found that during research of our heart rate and our O2 saturation data, that there are a number of individuals that had this very same problem. And a lot of it stems back to the fact that we used the manufacturer, which is Maxim Integrated Technologies. We used their function for processing the data. It appears to be overtly sensitive to variations in that data, and any small peaks beyond the larger peak, which symbolizes a heartbeat, also gets added in as a beats per minute calculation and causes the high 150 to 200 beats per minute numbers that we saw. So we may need to also implement a smoothing algorithm along with our own autocorrelation function to help make this data more usable. Finally, we find that the LoRa transceiver interface is something that we needed to focus more on. Although the Arduino is very helpful and there's a lot of makers and forums out there available for integration and use into a project, we realized that perhaps the Launchpad may be a better use for this because we know that it interfaces with the custom-built LoRa transceiver that we were provided by the university. The downside of using the Launchpad is that there's only one UART port, so we are unable to interface the GPS module with it, which is why we initially went for the Arduino Mega 2560 because it has a whopping 4 UART transmit and receive ports available on it with pins, which would provide us all the flexibility and the connectivity that we required. So unfortunately, we would have to use perhaps a SPI protocol to link up our Arduino with the Launchpad. And if that were successful, then we would have another pathway to transmit between the two, freeing up that UART port on the Launchpad and allowing for direct connection to the LoRa transceiver, allowing us to transmit our data. And in the poster, there are a few moments where we did call back some references, and those are listed here at the end. Thank you for your time, and we hope you've enjoyed our presentation of CLOVIDD. Thank you.